Hello, everyone, and welcome to the last installment of thinking about mixed models. And this will actually be the last time that we'll explicitly be thinking about general linear models or general linear mixed models as we know them. What we'll get to starting next week is start thinking about totally different types of error structures instead of thinking about normal. So today we're going to finish up and we're going to talk about something that is called, historically it's been called repeated measures. And again, this is really about the experimental design more than it is about the modeling approach. Repeated measures, as the name implies, refers to situations where you are taking repeated measures from the same subject or the same individual or the same plot. So in some ways it's, and as we'll see, it's very similar to how we set up the models when we had a blocked design or even a nested design. This is just a different name for the same type of modeling situation where we're going to want to make sure that we're paying attention to the degrees of freedom when we're doing our hypothesis testing and also estimating the uncertainty around our parameters. And so I've set up and I've cooked up, as I'm wont to do. Let's make me small. Bye, Jim. I've set up this scenario here where I just have some cooked up data, and let's just look at it and we can explain it. So what do we have here? We have an experiment where we measured something. We have 4 different treatments. We have a control treatment, drug A, drug B, drug C. And then we have subjects 1 through 10. So in this scenario, there were 10 people that were involved in this study. Each of those 10 people received all 4 of the treatments. So you could almost think about this as being a blocked design, except there's no replication within blocks. Each subject, so person 1 here, only one time received the control treatment, one time received the drug treatment A, drug treatment B, drug treatment C. So one important thing to kind of point out with repeated measures designs is that there's often this idea that the repeated measure has to do something to do with time. So early, mid, late, for example, if you measure the same individual, that would be something that oftentimes people would analyze as being something from a repeated measures design. There is nothing in the repeated measures itself, or at least the analyses for repeated measures that we're going to talk about, that explicitly accounts for anything to do with time. But you often see that in a lot of statistical programs where by default they're going to assume that repeated thing that you're doing within subjects is some measure of time. And again, the modeling is not going to take into account time as being an ordinal thing where time 1 comes before time 2 and time 2 comes before time 3. And so don't worry too much about thinking that it has to be about time. Actually, in a perfect world, like with our example here, where we have each subject is getting the 4 different treatment combinations, in a perfect world, you would randomize that for each subject. So maybe one subject would first have drug A and then drug C and then drug B and then control, and maybe somebody else would start with control and then B and then C and then A and so on and so forth. So I just wanted to mention that because a lot of programs like JUMP and a few other statistical programs, it just assumes that you're doing stuff with time. And again, that's not an uncommon thing for people to use a repeated measures design when they are measuring the same thing at multiple different time points. But I just don't want you to think that it has to have anything to do with time, because actually formally it has nothing to do with time. Okay, and so here are our data in long form, and we could you could imagine that maybe we would be tempted to just analyze this if we're interested in a difference of our response variable across these different treatments. It might be tempting to set up a linear model where y is some function of our treatment. So it might look something like that. We have our parameter estimates, and we have some estimate then of the effect of drug treatment A and drug treatment B and drug treatment C, all versus the control. The control would be the intercept. So it looks like all of these different drugs, there's an increase in the value of Y compared to the control group. But if we were to do an ANOVA on that, let's go ahead and do that. What we see is, first of all, we might have a big sad face because, oh, nothing significant. That was a lot of money and we didn't learn anything. But more important, we could look down here at the degrees of freedom, and immediately we should recognize that there are far too many degrees of freedom in this model for hypothesis testing. We only have 10 individuals in the study. So we need to account for the fact that really we have 10 experimental units in the study, and each of those experimental units received all 4 of the treatments. But when we ran this analysis of variance right here, it was not accounting for the fact that we only really had 10 experimental units. And we can set up the data a different way just to see just to kind of drill into our heads that this is individual 1. This is the response for the control, drug A, drug B, drug C. This is individual 2. Drug A, drug B, drug C, so on and so forth. So you can see when we set up the data this way, there's only 10 rows of data, and that's because we only had 10 experimental units. We only had 10 people in this experiment. And these kind of things are actually quite common in like the biomedical literature and things like that, because it's very expensive to maintain laboratory animals, and especially if it's trials that are done on humans. It's very expensive and very difficult to get the permission to do any kind of an experimentation on humans, and so you generally wouldn't be able to have the perfect design that you might want, which would be, you know, let's get 1,000 people and give 250 one thing, 250 the other, 250 the other, 250 the other, and have truly 1,000 independent observations. That's just not going to be realistic with the limitations of a lot of experiments. Okay, so that's what our data looks like, and we know that this ANOVA then is what we might think of as incorrect. And then again, we can maybe be sad about, you know, why are we not detecting any difference? And so what I can do is I'm just going to make a plot here so that we can plot out our data and kind of understand what it's looking like. So this is just the raw data that I'm plotting here for the control group, treatment A, treatment B, and treatment C. Okay, and you can see there's a lot of spread in these points, and so maybe it's not entirely surprising that we failed to reject the null hypothesis if there was any difference, just because there's so much variance there. We have very little power to detect what would relatively be a small effect size. And we can again remind ourselves of what the hypothesis testing was doing when we set up that ANOVA. There's the grand means for A, B, and C, and you can see that they're all pretty much right on top of one another. So again, it might not be terribly surprising that we failed to detect an effect. What we could also do is we could look at it using the interaction plot function, which I was trying to sell you guys on because I just think it's so neat. Where we have treatment, we have subject, and we have our response as Y. There it is as an interaction plot. There's all of our different subjects, and you can see like subject 9 overall is just higher than the rest of them. So what we want to do is we would like to remove all of that among subject variation when we get to the point that we're going to do hypothesis testing. Okay, and again, here's those means, and so again, it's not terribly surprising that we might not detect an effect. So by putting structure to the error and removing the effect of among subjects, now we're going to be able to remove that, and then we can think just about the variation that is explained by the drugs. And so for conceptual purposes only, and the code is included in the R scripts that I've given you, but I put in large, big exclamation points. This is only for conceptual graphing purposes. But what I'm going to do is I'm going to take each of these individuals and I'm going to center them around the mean. In other words, the mean across all the different treatments for each individual is going to be 0. And that's the way that I'm going to just for visual conceptual purposes, remove all of that among individual variation. And so what I'll do then is I'll have a plot where I have it centered now at 0. So I expect the mean of each subject, of each individual in the study, I expect the mean across all 4 treatments to equal 0. And we can go ahead and we can plot and see what that looks like. Okay. And so now you can see that, well, now it does look like the control is a little bit less than group A and B, and then C is up here a little bit higher. So just by centering things, we're now able to visualize that there actually is a bit of a difference there, and that's because we've gotten rid of that whole effect of, you know, whoever it was, individual 9 up here being way higher than everybody else, and then individual 8 being really low. What we want to do is we want to just remove the effect of all that among subject variation. Right, okay, and so let me, I'm going to change this new data into a long vector. And so there is that's our centered data now. And I'm going to go ahead and I'm going to do an ANOVA on a linear model where my new data now, which is the centered data, because again, we're only doing this for, you will never do this, I hope, treat. But we can understand then, now this is doing the analysis on the centered data. So we've transformed our data by centering it for each individual. And we go ahead and we do that, and I get the same annoying warning messages I seem to always get. And so now we look at this and, you know, well, the p-value is significant now, which it wasn't before, so that might make us feel good, but we should still not feel too good about this model because we still have 36 degrees of freedom in the model. And that's because we're running the analysis on those data, but we're not accounting for the fact that we've already estimated 10 parameters in order to center that data. The only way that we could have centered that data would be to calculate the mean of each subject. And so what we want to calculate then is the correct degrees of freedom. And we can do that by saying, all right, what are we starting with? We're starting with 40 total observations. Okay. We're going to lose 3 degrees of freedom because we have 4 different treatment groups, right? And it's always the number of parameters minus 1 is going to be the degrees of freedom for the model part of our model. And that's because the intercept is sucking up the control group, and then we have those 3 parameters that are a reference to that. So we're going to say 40 minus 3. And if I were to do 40 minus 3, yep, that's fine. And then I'm also going to always going to lose 1 degree of freedom because at some point I had to calculate the grand mean in order to figure out the sums of squares. So this is the same as when we did any kind of multiple regression. And sure enough, if I run 40 minus 3 minus 1, I have 36 degrees of freedom in the residual, which is the exact same thing I got up here in that model. Okay, so we know where that comes from. But again, the one thing that we haven't accounted for in doing all of this is that we've already estimated a bunch of other means when we did the among individual component of the variation. And so we estimated 10 means, 10 parameters, 10 minus 1 is 9. So we're going to additionally remove from this 9. Nope, that's 6. That's a 9. There we go. Okay, so in principle now, that should be our correct degrees of freedom, which means that if we wanted to calculate the correct mean squared for the residuals, we would take the sums of squares associated with the residuals, but now we're going to divide it by 27. Okay, so that is what our appropriate mean squared should be for the residual term. And we can remind ourselves, it's always good to remind ourselves where this f value comes from. And again, we're using the f value to do the hypothesis testing because it's a variance component problem. And so that f value, again, comes from the mean squared of our model divided by the mean squared of our error term. And that's where we're getting that 8.1225. But again, this is the incorrect mean squared because the degrees of freedom here are incorrect. This is the actual correct mean squared that we want. And so let's go ahead and pop that in the model. that is our correct F ratio. That is the F ratio that we would potentially want to use to do hypothesis testing. And we can even take that F ratio and put it into the cumulative distribution function for an F. So it's going to be that, and there's going to be what? 3 and 27 degrees of freedom, and lower tail will equal false. And then here we have 0.002644282. That is the correct p-value, as long as we're happy that that's the correct way to calculate the denominator degrees of freedom. And so clearly you would never do this by hand. I only went through this exercise so that everybody would understand what the consequences are of adding that structure to the error term. We're removing that among subject component of the variation, and we're not using that as the denominator when we're thinking about what portion of the variation can't we explain, because that's where our statistical hypothesis testing is going to come in. So there's a couple of different ways that we can approach this. I'm going to just set it up as a mixed model approach. I will mention that in older literature, and by older I mean even literature that's only 15, 20 years old, which I'm sure to you guys sounds pretty old, but to me it just makes me feel old, is that people used to analyze a lot of these types of models using what's called a MANOVA, which is multivariate analysis of variance. Multiple analysis, yeah. It uses a multivariate normal. People don't really do that anymore, so I'm not going to really talk about that. It's again one of these things where I wanted to mention, because you might find older papers where people are in principle doing a repeated measures design, and they're giving you output that is entirely new and unfamiliar to you. But people don't really do that much anymore, and I think it's because they don't really feel comfortable about the underlying assumption of what's called multivariate normality. And the accepted way that people like to deal with it now is to set it up as a mixed model. And so I'm going to do it two slightly different ways. First, I'll do it not explicitly as a mixed model using that Elmer package, but I'm going to basically redo what we did right up here. If you recall, there was that AOV function which we had to use for one of the post hoc tests, I believe, where it's another way to keep track of all of the information that's in an analysis of variance, but it doesn't explicitly give you the hypothesis testing at the end. And that function was called AOV. So I'm going to create an object called AOV out, and I'm going to say it's an AOV. And I'm going to say that y is some function of my treatment, so that's consistent with what we did before. But then what you can do in the AOV function is you can be explicit about your error term. And then what I'm going to do is I'm going to say that that treatment is nested within subject. So that's what that syntax is telling R. It's telling me that I do indeed have an error term. You're always going to have an error term. But for this particular error term, I'm going to assume that each treatment is nested within each subject. So I can go ahead and I'll do that. And now if I take the summary of that AOV out, I want to point out that, okay, it's telling me what's going on in the error term. There's that degrees of freedom that we thought about. There's 10 different means. The number of parameters was 10 then. 10 minus 1 is 9. That's how many degrees of freedom are associated with that one particular part of the error term. And then here is the hypothesis testing part. And what you'll note here is that this is the exact same mean squared we got when we did it by hand. And this is the exact same F value we got when we did that by hand, which was there. And then again, we did the same p-value. And so this AOV method, which is really kind of the older school method, but as we'll see, it really doesn't matter, of dealing with this, is the exact same answer as we got when we decided, you know what, let's center all of our data, let's cheat and just do that on the front end, and then just keep track of our degrees of freedom. By explicitly telling the AOV function that we want to put structure into our error term, it's doing the exact same thing. Okay, so now let's welcome ourselves to the early 2000s, which just seem to be doing great for us at the moment, and set it up as a mixed model. And so I'm going to go ahead and I will load in that package. I'll go ahead and load in Elmer test. And I'm going to now make a mod. And so let's think about how we've set up the other mixed models. And this is going to be the same underlying philosophy that we're going to do, is that we're going to assume that each subject is different from one another, right? We know that one subject 9 was way up there and subject 8 was way down there. And what we're going to say is that we would like each subject to have its own intercept. And again, that's just our fancy way of saying I really want to put error to I want to put structure to the error term, and before I do my hypothesis testing and my parameter estimation, I want to remove that component of the error or the residual that I know that I can explain that portion of the variation. So it's the part of the error that I can explain, so I don't want to treat it as the unexplained part of my error. So it's the exact same thing that we did when we did the block de novo, which again was just a linear model with the organized error structure, and the exact same thing we did when we did a nested ANOVA, which again is just a mixed model. Okay, so let's go ahead and let's do that. So I'm going to say that my model is going to be an Elmer, where y is going to be some function of treat, and then I'm going to say I would very much like it if each subject got their very, probably should spell that correctly, if each subject got their very own intercept. So I go ahead and I do that, and now I can look at the summary of my model. Okay. And so again, we have the same kind of standard output as we had before. I'll just look at this variance component. Recall that we can say, well, how much of all of that variation that we couldn't explain in our model, how much of it was actually because there was just all this among subject variation? And we could do that by just saying, well, what fraction is our subject variance versus all the variance? And what do we have besides annoying error warning messages? 98%. So that means when we set it up as kind of a traditional linear model and we ignored all of the non-independence of the experiment being done within each subject, if you recall, it was not significant. And I jokingly said, oh, we have a big sad face. Here it is right here, right? So even though we got more degrees of freedom, we are still getting a really high p-value, meaning that we're unable to detect an effect. But that's because, again, when we're doing the hypothesis testing, we're looking at the ratio of the error term versus what we can explain with our model. And we have a lot of variation in the error term because there was a lot of among subject variation. And in fact, 98% of that variation in the error term was due to among subject variation. And so by removing that, now we have relatively a small amount of error that we're unable to explain with our model. And so let's go ahead and we can run the ANOVA on that. And then here we have it. Look at that. We get the exact same answer as we got when we did it as an AOV. And we would get the exact same answer if we went through Jim's long convoluted way of centering all the data and then calculating the F statistic by hand, which again is something you shouldn't do. But hopefully if you rewatch that part once or twice, you'll totally get what this is doing behind the scenes, which again is removing that part of the variation that we don't care about when it comes to hypothesis testing. If we're interested in how the drugs are different from one another, I don't care that subject 9 was much larger than subject 8. What I want to do is I just want to remove all of that variation, and that's what we're doing here. Okay, and so we could follow that up then. Oh, I do want to remind everybody that when we're doing the ANOVA here, and we're getting this output, that's because we are using the package called Elmer test, and Elmer test is assuming that we know the appropriate denominator degrees of freedom. And there still is an active argument in the community about whether or not that is the appropriate degrees of freedom. And we could even look at what the output would look like if we had just used the LME4 package, which was the very first package that we started playing with when we started doing these models. And so I can do that. Let me call this LME4. So this is a way in R where I can say I don't want to use Elmer Test's version of Elmer. I want to use the version of Elmer from LME4. And again, there are two functions that are called the same thing, but Elmer Test overwrites the version that's in LME4. And I apologize if that's confusing. I'm not the one who wrote the packages. But this is using, if we just use LME4, and then if we were to do an ANOVA on this, I just want to remind you that we wouldn't get a p-value. We would still get the same mean squares, we would still get the same sums of squares, we'd still get the same f value, but we would not get a p-value. And the reason why we wouldn't get a p-value is that the original authors of the LME4 package decided that they were going to be conservative and not get in arguments with people about what the appropriate denominator degrees of freedom are. Again, either method is entirely valid in the current state of the art in statistics today. As I think I've mentioned before, in statistics, there's no one right way to do something often. There's clearly lots of wrong ways to do something, but there's no one right way. And mixed models is a really good example of there not being one accepted right way. But if we were to stick with this LME4 object, we could again use, let's open up the car package, and if we were to use the capital A ANOVA on that, we would get this walled chi-squared test. And we could likewise take our object that was made in the Elmer test, and we would get the exact same answer. So the capital A ANOVA doesn't care whether or not you use Elmer test or whether or not you use LME4 when putting together a mixed model. And then of course the last way, let's just make sure that we are all good here. We could also create a reduced model. I'll call it .r, where all we're doing is estimating the error. And then we could compare that reduced model with our more complicated model, and there would be the associated p-value with that. What that's telling us is that the model that included treatment is a better model than the model that didn't include treatment. So again, here's the three kind of standard ways in which we can do hypothesis testing on such a mixed model. We can either use the Elmer test function, which does it in more of the traditional way, where we assume that we know what the appropriate degrees of freedom are for the denominator. We can do it as a likelihood ratio test, which is what we've done right here. Or we can do it as that other variation of it, that walled chi-squared test, which is just another kind of flavor of a likelihood ratio test. And then I guess finally what we could just really briefly revisit is we could find out where those important differences are. So up to this point, what do we have? I got to find the name of the library or else I'll get lost. It's library multcomp. That's what I wanted. So we can now do post hoc tests and ask where are the important differences, because all we've done thus far is we've done a really good job at, first of all, modeling it correctly, where we have the appropriate where we can do the appropriate hypothesis testing and conclude that indeed there is a difference somewhere between the control group and treatment A, treatment B, and treatment C. And so we could use the multcomp package, and we could start with, if we wanted to, we could do a Tukey's HSD. So that's the standard standby that people seem to like for doing hypothesis testing. And we're going to do it on our mod. And then what are we going to do? We're going to do these multiple comparisons, where treat is going to equal, and then we tell it that we want to do a Tukey test. Right? So it's just like we did when we did just standard post hocs with ANOVAs. And so there's that. And then if I were to take the summary of that, we can now look at where those differences are. And so it looks like control and drug A are different from one another. If we are dead set on our alpha of 0.05, drug B is not different from the control, but drug C is different from the control, and we're not detecting any differences among the different drugs. There's a pretty good chance if we were actually analyzing these types of data that the Tukey probably isn't the most appropriate test to do, because, well, it might not be the most appropriate test to do, because we might just be simply interested in whether or not any of these drugs are better than the placebo, than the control group. And if we wanted to do that, then we could set it up as a Dunnett's test. And so let's go ahead and create an object called Dunnett's. Dunnett. Oops, spell it right. And then here in parentheses, we're going to tell it that we want Dunnett. So remember, what Dunnett is going to do is it's going to take your first factor level and it's going to compare everything just against that. Because of how I've put in these the names of the different treatments, control starts with the letter C, which means that it's going to come before drug A, drug B, or drug C. So we're going to compare everything only against the control group when we do this. And we'll go ahead and we'll do that. And now notice that they're all showing up as being different. It's a more powerful post hoc test because we're doing fewer comparisons. And the fewer comparisons that we do, the more statistical power we're going to have to detect an effect. So if we had set it up as a Dunnett's contrast, then we would say all the drugs are better than the control group. And then we could, interpret our effect sizes. And, on average, it looks like drug C is the best. It's 0.44 greater than the control group. It's almost twice as good as drug B compared to the control group. And again, that's all just about how we're choosing to interpret our hypothesis testing at the tail end. Okay. And so again, that ends up, that finishes up looking at putting structure to our error term, and that's really what mixed models are all about. And hopefully, if you go back and you kind of focus in on the blocked design, the nested design, and the repeated measures design, you realize that all these models are essentially doing the same thing. Basically, we're keeping a close eye on what our true experimental units are and what the appropriate level is for us to do the statistical hypothesis testing. And so in the blocked ANOVA example, we simply tried to remove the variation that was due to among block variation in order to do our hypothesis testing. When we did it as a nested ANOVA, we wanted to account for the non-independence of the observations within a particular hierarchical level. So whether it be 5 seeds from a given plant, for example, we wanted to account for the non-independence of that. So we allowed each plant to have its own intercept. And then here in this example with the repeated measures design, again, you can think of that as just simply being a blocked design, but there's no replication within blocks. And then we're setting it up the same way. We're going to allow each subject to have their own intercept. So not only by doing that are we modeling things appropriately, which is always nice to feel as though you're modeling things appropriately, you are also accounting for the fact that you can actually put some structure into that error term, which in principle should increase your statistical power to make inferences where maybe you can decide that certain things are important or are not important for your response variable based upon the parameters in your model. So on that, I will say have a fantastic couple of days. And what we will start on next week is we will start on what are called generalized linear models, where again we're gonna push all this normal stuff to the side and do things that are maybe more appropriate if you have different types of data. So we'll start next time by revisiting our friend the binomial distribution, which I'm sure everyone has missed a lot because it's been months since we've talked about the binomial, and don't want the binomial to feel lonely, so we'll revisit it. Okay, Cheers. Have a good one. Stay safe.